Welcome back. I'm Chris Sikora, and I'm going to step you through exercise 7 for Inventor 2021. Now, for my sim class, essentially, this is what they call computer-aided engineering, or CAE. We're going to do a stress analysis on a bottle opener, and that's what you're seeing up on the screen right here. It's animated, and we could actually see where stress is occurring on the surfaces. And it helps us to determine whether or not our part design is valid. And usually, if you're going to do this, it's good to have the mathematical knowledge so you can actually do some hand calculations just to verify it. This is, as long as you put in the good information, and this is actually even more detailed than what you can do via hand calculations, typical hand calculations, that is. All right, so let's get started here. This is a bottle opener, and you can see I have it animated. We're going to learn how to do that. And if you're wondering, this is in the training guide, which if you go to the vertanux1.com one page, vertanux1.com, go to instructional manuals, and you'll find the Inventor manual, the green one right there. Bring that up, and then get to page 69. Now here you could actually see our design. We're going to keep it quite simple. We'll actually even make it more simplified than this. And we're going to start off in metric 2, just so we could get megapascals or MPa, as you see here, for our units versus PSI. So let's go to New up here, and make sure you go to Template, hit the little arrow here, English US, and then click on Metric, and then find the standard MMI part. Now you could create it in inches and then change it over. That's in there too. If you ever need to do that, it's just under I believe Tools and Document Settings, and then Units, and you'd be able to change it right here. So just be aware if you wanted to build something in inches and then convert, or vice versa. All right, but let's get started drawing that. Now the geometry in the book, training guide, you can see here it's a 1/2 inch in height, 2 inches across, and then the rest of it we'll just have a little fun with. So click on Start 2D Sketch, select your XY plane, and go to the Line tool, and right at this origin, click and drag it up. Now, remember we saw it was a 1/2 inch versus this is metric. So let's go ahead and type in 0.5, but type in IN for inches, and hit enter, and it automatically does a conversion for us. See, it's 12.7. Let's go ahead and go across here, make sure you're at 90 degrees, and we're going to type in, this is supposed to be 2 IN, so 2 inches. Hit enter, and there it's 50. All right, now for the rest of this, we could just click on front here and close it up. And I'm going to give you some freedom to make your own bottle opener here. So click here, and maybe about 4 millimeters in, like so. Drag that in about maybe 8 to 9. Click. You can follow perpendicularity or an angle, or if you want, put a fillet in there, but we'll talk about that in a second. When it comes to geometry like that, you don't always want. Go ahead and drag this out, connect here. We'll make a small little jaw here. Click, and then bring this up about there. And again, you have freedom to do what you want here. And I'm going to make the area where the finger is going to pull up on it. So I'm going to put this nice little angle right here. Click, and then there, click, and close that. All right, so I line chain. Make sure that these points are here. Those of you who are still new to Inventor, you got to have that line in there, even though it doesn't look like it's needed. There it is. Okay, now the question comes up, feature or defeature? Now, defeaturing is very common when you're working with computer-aided engineering, or in this case, a finite element analysis. And what it does, finite element analysis, breaks up your model into a collection of polygons, whether it be triangles on some systems, some could set it to a 4-point rectangle. But anyhow, when it comes to that geometry, mathematically behind the scenes, it calculates what's called nodes, or the elements, which are the corners of each one of those polygons. And as a whole, it could actually calculate where the highest amount of stress is going to occur, and whether or not, depending upon the material information you put in, if it's going to be a valid design. If it's going to be too weak and possibly break or fail, and or if it's going to be over-engineered. Maybe it's too much material. You can reduce that. Now, do I want to put the little hole here for the keyring? We could. Most people would tell you, anyone who's done this for a while would probably just leave it off. Or if it's already modeled into the part, which that's mostly the case, it might be suppressed. But we could put it in. The first FEA analysis I've ever done was back in 1995 on a computer that was equivalent. I mean, your wristwatches now are more powerful than that computer. It was a Spark Station. I can't remember which version, but it was very expensive, and it had 24 megabytes of RAM, so very lean. We did something not all that dissimilar to what we're doing today, an analysis, which today, by today's standards, is very simple. And it's going to be able to do this within seconds. But it took 8 hours to do back in those days because it takes up a tremendous amount of system resources when you do finite element analysis. So it's good to have a hardy computer when doing this. But to keep the features off not only helps keep it within the boundaries of your hand calculations to match up, because if you've ever seen the engineering books, it's all math, of course. And they're generally dealing with two-dimensional planes when you're doing something simple like this, or what's called a linear analysis. And linear analysis is desirable for simple parts such as this. Other parts, not so much. You might want what's called nonlinear, and that's an advanced stage we're not going to cover today. But anyhow, so let's go ahead. We're not going to put the fillets in because they're just not really necessary all the time. If it is a structural fillet, then yeah, but we don't really need it on this one. So let's go to 3D model and go to extrude, select this profile and have it go symmetric. 10 millimeters is fine, hit OK. And again, we don't need to put in any of the fillets. You could, but you don't need to. Just it actually slows things down. All right, now we're going to set this up. So we go to, first of all, let's select the material. So up here, this is your actual material library. And if you look this up, you'll see there's plastics and all sorts of things. Now, each one of these materials has a rating that you could look up. You could actually Google them, and you're going to see, like, for example, we're going to pick an aluminum, and we're going to pick 6061. Now, 6061 aluminum has some variants. There's T6, there's T4, there's the way they're hardened, or they're and essentially if they're age hardened, things like that. This one is your basic 6061. If you were to look it up, we'll actually see what it's going to give us here, but let's click on aluminum. Now go to environment and click on stress analysis. Now some of you may not have stress analysis. It comes with the student license for home, so you should have it as long as you install the Inventor Professional, which has all the modules. Now, the educational licenses typically have that too, but I found the college that I teach at, quite often our IT department just goes with the basics. They don't install everything, and I found that it hasn't been installed before. So I would check on that with your IT department if that's the case, but it just might not have gotten loaded, and they should be able to load that up for you. Go to stress analysis, go to create study, and here we could give a name to this study if we'd like. There's some parameters in here I don't want to go through because they're some of them get into more advanced techniques. We're going to go ahead and actually just stick with the defaults that we see here. Go ahead and hit OK. Now let's go to assign. Now we already assigned a material, but this is where you could change that. You could go to materials and see a much more detailed catalog of these materials. As you hover over them, you'll see the part adopts the visual properties or characteristics. But we see there's different types of 6061, but this is the one we picked, and it's already up there. We're just going to double click on it, and you'll see its identity. And like I said, 6061 in its basic form is aluminum, magnesium, silicone. It's an alloy. It's pretty strong, much stronger than a typical aluminum like a 10 series. We're going to go to, there's appearance, which you could adjust if you want, but there's physical, and you'll see there's lots of information in here. And you could customize this and make your own materials if you have a variant of it, because they don't have every single material in here. And I believe you can probably find materials library online, maybe for a purchase. I'm not sure. But anyhow, here you could actually see we have yield strength and tensile strength and so on and so forth. And depending upon your calculations, this is in PSI. You could actually do the conversions if you like PSI into MPA on Google and get that feedback on what that is. But typically, when it comes to yield strength for 6061, if you're talking MPA, it's between 100 and 130 or 125, I believe, without doing the hand calculation. If you're talking 6061, which is T6, for example, that's considerably higher. That's 275 megapascals. That's its limit. Now, when I give you those limits and you look those up for megapascals or PSI, essentially, when we're talking about that, we're talking about yield. Yield doesn't mean it's actually breaking or rupturing. It actually is typically an indicator that you've bent something beyond its limit of flexibility, and it's going to what they call the elastic limit. And you've gone into what they call the plastic range. And once it's in the plastic range, it's not bending back. So we refer to that as failure if it doesn't bend back. So if you pull on something like, let's say, this is a metal and I pull back and it bounces back, you've not met yield yet. And whatever the yield might be, like in this case, it's 3.989 for the yield strength in PSI. Now, once it gets past that or hits that or gets past it, if you bend it, it doesn't bend back. It stays permanently bent. And so, again, that's why they call it failure. It doesn't mean it broke, but it did bend. And just be aware when things bend, many of you in engineering know this already, if it gets strain hardened, especially if it's a metal. In strain hardening, you'll find it's difficult to bend it back, and then you've just created a whole nother issue. So moving along here, we're just going to keep this as is. If you want, you could do that conversion on there. But we know it's over 100, around 100 or over that we're looking for if you're talking MPA here. Okay, now let's go to, let's see here, we want fixed. Now the constraints are what you want to add. And I typically like to add them first. You don't have to. But the constraints are like how it's going to be held. Where is it going to be the immovable fixture? And this is with linear analysis. You have to figure out where. Now, on a bottle opener, the whole thing is really in a dynamic state moving. But there are some areas that probably have the force applied more than others. So we know that this surface here is where we're going to be applying the force. We're going to be pulling up on that. But the jaw is an area of interest because the very top of that is actually on the top of the bottle cap. So that might be a good place to actually put our fixture. Could you put it on the underside? I've talked to a variety of engineers over the years, and it's like, well, some say, yeah, some say, oh, it'd be more comfortable on top. It's not always just black and white. There's actually variables there that you have to consider. So I'm going to go ahead and just select that face and hit OK. Now we're going to add the force. Now notice there's force, pressure, gravity, and there's all subsets too of things that you could apply. But let's go to force right here. And you'll see the magnitude, how much in newtons. Now, those of us in the United States aren't used to dealing with newtons. When we step on a scale, we're used to seeing pounds. And so what we can do is a conversion. And that's why I had Google up here. You could type in like, let's say we wanted to test 10 pounds for this to pop open that top. So 10 pounds of force. And see 10 pounds is equal to N. You can type that in. And it'll give you here 10 pounds is equal to about 44.48 newtons. So let's go ahead and put that in. 44.48. Okay, and hit enter. All right, and now we have to select the location. So the location is right on that surface there. Again, our finger's going to be under there pulling it up. Hit OK. Now we're ready to run the analysis. Now, there is a mesh value that we probably want to tinker with here because this is a very small part. go ahead and hit simulate, and we'll first take a look at what it's going to do. Hit run. Okay, and we see the simulation there, but let's take a look at what the mesh looks like. Now, the mesh is the collection of polygons, in this case, triangles that it's using, which all those 3 points are nodes, or that's part of why they call it finite element analysis, because they're elements. And you can look up that more detail if you like. I'm not going to go into it right now because it goes on. I mean, people get degrees in this, so just be aware. It's not something that you just learn everything right away. All right, so we see here, these are very large polygons. And sometimes you might want a little bit more detail than that. In this case, we're getting an average of 36.83 maximum MPa. Now remember, our limit is well over probably 100 for the megapascals on this material. And again, we could look that up if you ever type in, there it is, aluminum 60, 61. We're looking at megapascals here. And here's just some averages. The tensile strength, you'll see here 124. That's not saying yield strength, so yield is usually below the tensile. But we're at 124, so approximately. All right, but let's adjust this a little bit. I want to get a more detailed interpretation of what's going on here. So that's where the mesh comes into play. And you could go to mesh settings here. Now, if we look, it's at 100 thousandths for the average element size. Let's squeeze that down a little bit. That's a little bit on the big side here. And we'll put in let's try 0.02. Okay, and the minimum element size. Let's go ahead and put in 0.01. Now this is probably too much detail, but let's go ahead and see what happens here. Hit OK and run the simulation again. And watch the polygon count. It'll increase dramatically. Okay, now not only did we jump from almost 40 to 89 max, but it's pinpointing the regions that are experiencing it, versus the blue were really well in any range. And in this case, just that little area there, we're starting to see some red. So there's really not much going on here as far as it's very strong, i.e. it's very strong. So even with the mesh set to a finer detail, we could see that. So as you can see, mesh is very important. Now, we could go to animate here and hit play, and you could put in how many steps. If you want it really smooth, put in 30. If you want it, 10 is fine, that's good too. And you can see as it's bending. Now, it's important to note that this is an exaggeration by default, unless you set it up differently. And you can see this is the adjusted display, and it's set to X1. But let's see the actual movement. The reason they go with that is because in many cases, you wouldn't even really see the actual movement. Like here, you can see it's very small. It's barely moving. So that's why you'll see them exaggerate it. And also, you want to see what direction it's moving. Is it actually twisting or contorting, in such a way? So that is something of interest. Now, speaking of the displacement or the actual travel, you could see by double-clicking on displacement here just how far it is moving in a visual spectrum analysis. So here we see in metric, it's only moving 12 tenths of a millimeter. So it's barely moving. That's why you have that exaggeration on there. And so let's turn it back on. You'll see if you adjust it even more, you can see it moving, but for the analysis purposes. Okay, so, but still, we're not going to talk about first and third principal stress, but let's talk about safety factor. Now, safety factor, or factor of safety, is a way of testing your model to see if it's within limits. Now, each industry has their factor safety that they typically use. Like the automotive industry uses a factor safety of 3. That's times the amount of strength that they would want or endure. And here we're actually seeing the 3.09. It's hitting right at that. So that's actually a valid design if you're designing it with that intent for the automotive industry. Be aware, though, that like the aerospace industry, remember, they have to launch things into the air, and the heavier it is, the less efficient it is. And so they might actually work off of a 1.5 factor of safety. So this is twice that. So it might not be desirable. So, well, it's too thick. Let's thin it out. Let's change it. But let's go back to the von Mises stress here. And let's talk about whether or not this is a valid design as far as it's structurally sound. It's going to be within our limits, easily within our limits. But if we're looking at around megapascals, about 125 or so, that's way up here. And this maximum of red that we're seeing, it isn't bad. That's fine. We're not even reaching that limit. So essentially, when that's getting bent, there's no yield occurring where it's actually bending and not bending back. Everything is going to flex right back into its shape. It's only moving that 12/10 of a millimeter. So it's a very good design. However, it might be over-engineered. And if it's over-engineered, that's money, okay? You have to balance that. Now, safety should always come first, but cost should come second probably at that point. So we might want to thin this out. And so you could go back to the modeling here, go to 3D modeling, and you could actually make changes to it and then update it. So if we were over here, we're still, I have to turn off finish analysis, sorry. We can now go over here, we can make changes like if we were to edit the sketch. Let's see here, click on edit sketch. Now I'm going to drag this up and make it thinner here and there. And actually, let's do it in all areas and see what happens here. Okay, much thinner. Hit finish sketch. Now we could go back to the environment stress analysis. And let's go ahead and hit simulate. That's going to remesh it and calculate. I'll hit run. All right. Now we're starting to see some issues here. We're at 382, and remember, about 125 is our yield, so something might be bending, although, look at the colors. It's bleeding through, so it's blue right there. It's actually not bleeding through, so technically the core is still intact and probably just surface transformation where you're getting that yield to occur, probably. But let's look at the displacement. And as far as displacement goes, we're now seeing it's moving almost a millimeter. So turn off adjusted, go to actual. So it is bending a little bit. But boy, we're actually not doing too bad here, even as thin as the part is getting. Let's take a look at the safety factor. And the safety factor here is well below, probably, if we're looking at a safety factor of, if we want for automotive, if we were supposed to be staying at a safety factor of 3, look at our 0.72, not good, so it fails. All right, so there's a lot of those different variables that you have to take into account when you're looking at factors of safety. And so just be aware when you do that, there's liability involved here. Someone, in this case, most likely no one's going to hurt themselves, you would hope. But when you're designing something for a car or train, plane, you have to take into account these things. And also imagine the amount of money you could save by designing it so it's not using as much material. Multiply that by 1 million parts that you might make, and how much like if you removed 30% of the material cost. It's a lot of money. So again, safety should always come first, then look at the actual ramifications of a cost. And that concludes this exercise. Oh, actually, I meant to show you, typically what you want is, you want a report. And I want to show this, is really nice. Usually you don't just leave the model as is. You create a report that someone could read, and it has all the information. So click on report here, and you can put in any sorts of information like the author, the part, the company name, whatever you're doing there. and there's properties and studies. You could customize it. Just hit OK here and look at what it's doing. It's taking snapshots of all of the different images of this. And it generates a nice report for you. Look at that. Even cost could be a factor that you could apply with this material and figure out how much it's going to cost due to its weight and the material that you selected. And so there is a nice report. Now, when I worked in industry, we would actually, this is a great report, actually didn't used to produce them quite this nice in the software that I used to use, but we would actually do it Microsoft Word. And you could go ahead and you take pictures just like you have there. We wouldn't give all those images, but we would take the ones that we could describe and with a paragraph put down what we're actually seeing, just like I was explaining to you reasons why for these things. Some customers like that, especially if they didn't have the engineering background to interpret what they're reading here. You might need to help them along, but just be careful, because if someone is hiring you to do this, make sure that they're not hiring you to be their insurance policy. So if it breaks, again, there's liability involved. So just always keep that in mind. And that concludes this exercise.